Okay, are there any questions on what we're doing? Any questions? Right. Can anyone talk a little bit about what we're doing? Does anyone know what we're doing? Yeah, Claire.
We're doing the first derivative test.
So the first derivative test. So what's the idea?
So basically, if we have a function f of x, we can find where the critical points are, so where the derivative is 0 or where it does not exist.
Okay.
And then we plug those on a number line.
Okay.
And then we find out where in those little, in between those points, the derivative is positive or negative.
Yeah, yeah.
And then based on that, that basically means where the function is, f of x is increasing or decreasing.
Yeah.
At those points, it could change from increasing to decreasing or decreasing to increasing or not change, and depending on that, that's how you get a max or min.
That's right. Yeah, Mariah.
There's like that way, but then
Yeah.
like also like is plugging the critical points back into the original function a way?
Yes, it is. So the game is right. Trying to find your maxes and mins.
Yeah.
Right. The trouble is this. Suppose you have something like this. Okay, it's on. It's on a closed interval. You have this is, and so you run through the whole procedure. You say, okay. There are only a few possible places where maxes and mins could occur. One is here, one is here, one is here, one is here, one is here. So these are the four possible places. These are the only places where maxes and mins could occur. Okay, and then you say, okay, maybe you don't know what the graph looks like. Okay, but it turns out that here and here you have a derivative of 0, and these are the endpoints, so these are the critical points. Okay? And then you say, okay, I know that my function being continuous on a closed interval has a global max and a global min. So you plug in each of these places, right? So let's call this one C and D. You plug in these points, and you find out that, oh, okay, this is the lowest value. The lowest value is at A, and the highest value is at B. Okay, so that would allow you to find the global max, right, and the global min. You'd say this is the global max, this is the global min. But then C and D, when you plug them in, you'd say, oh, these are not the global max or global min. But that's the only information you'd have at that point, right? Because because you're unable to see it.
Okay.
Right. If you're, maybe if you're lucky, it's a simple function and you can see it. But maybe it's not so simple and you can't imagine it. Or maybe it's in higher dimensions. It's in many more dimensions and you can't imagine it.
But if the derivative is still 0 at that point, wouldn't they be like local mins and local maxes?
Not necessarily, right? Because you could have something like this, right?
Okay.
Where it becomes where the derivative is 0 just for a second. For example, x cubed.
Yeah.
Right? If you look at x cubed, then its derivative is 3x squared. So that would say, okay, well, one possible place for an extrema, or the only possible place for an extrema is here, right? But there is no extrema, right, for this function. Right? For this function, there's no local max, no local min, no global max, no global min, right? Unless we restrict it to an interval. Yeah, Claire.
So what happens if there's like an asymptote at C and the value, like what would happen then?
Yeah, so
If you're plugging into f of x.
So it could well happen that your function is discontinuous, right? Your function could be discontinuous. So are you saying if you have something like this, then there's no global max?
Okay.
Is that what you're saying?
Yeah.
Yeah, certainly that can happen. There might not be a global max. The only reason we knew there was a global max here was because your function, because of the extreme value theorem, which said that if you're continuous on a closed and finite interval, then you're guaranteed a global max and global min.
Okay.
But this function doesn't satisfy the extreme value theorem. So the extreme value theorem doesn't tell you anything about this function.
Right, and
You're
if
not guaranteed a global max or.
And if you plug in C, you'll just get does not exist. Or,
Yeah,
you know,
there's no value for C.
Okay, so that won't like change anything.
Is it still a critical point? C.
Is C a critical point? I mean, not exactly, because the function isn't defined there, right?
Oh, it's not undefined.
The
So
function's
it
not
has to
defined
be
there.
0 to be a critical point. It can't be undefined.
Yeah, it has to. I mean, well, you're looking for a place. What's a critical point? Well, either the derivative is 0 there, or the derivative is not defined there.
Oh,
Okay.
yeah, okay.
But here it's even worse. It's not just that the derivative is not defined. The function's not defined.
Okay, I see. Yeah. Okay.
Yeah.
That makes sense.
Yeah. So, if the function were defined there,
Mhm.
then it would be a critical point, because you'd say, okay, this is the function is defined there, but doesn't have a derivative. Okay, and indeed, look, this C does turn out to be the global min. Okay, C could turn out to be a global min. Okay, so getting back to Mariah's original question, you see that we really do need the first derivative test, or knowing the first derivative test actually does help us, because it tells us where local maxes and mins are. Right? It will say this one is a local max and this one is a local min, and that's something that you can't determine just by evaluating. Right? If you just evaluate, you have no idea what these things are. Okay. So yeah. So the game is trying to find where maxes and mins are. One can sort of find this game in applied problems. So 4.4 sort of applications of optimization. Really, I think of this section as a bunch of disguises. So you have there's a mathematical problem, and then somebody puts some disguise on top of it. Okay, and what your job is basically to peel off the disguise and find the mathematical problem, and then just solve the mathematical problem. Okay, so here's an example of one such problem. So what number in the non-negative real numbers exceeds its cube by the greatest amount? Exceeds its cube by the greatest amount. Okay. So you've taken a perfectly good mathematical problem and translated it into English. Let's translate it back into mathematics. Okay. So how do we translate this back into mathematics? What number exceeds its cube by the greatest amount? Exceeds its cube. So what are we interested in looking at? Take 20 seconds and maybe think about how you would approach this problem. Or a minute.
Oh, greater field. Okay, turn to somebody next to you and say what you're thinking, what your strategy is. Past this, the y-axis, and make people left. Thank you. I worked really hard on this.
Okay, would anybody like to say anything? Like what you're interested in? Sarah, yeah.
Well, I would define the function as x cubed.
The function, so you're looking at f of x. Let's let f of x be x cubed. Okay?
And then you're trying to find like the global max. Or sorry, not the local max.
So you want the max of f. So what would that be? That would be the greatest value, the greatest cube, right? So that would answer the question, what number has the greatest cube, right? What number has the greatest cube? But the English is, what number exceeds its cube? Exceeds its cube by the greatest amount, right? So it's not quite that that would be what number has the greatest cube. Okay. So Megan, yeah.
I don't know if this is right, but would it be like the greatest slope, so we find the greatest derivative, the difference between x and y, or is that not right?
So what function are you?
Sorry, if you find the derivative of x cubed, then you find the maximum of that by finding a second derivative? Is that wrong?
Okay, so then what you're saying is that, so what you're saying is that let's look at rather 3x squared and let's maximize that, right? So that would, what would that be? That would be, well, I don't know how to describe this, but, so here's x cubed, and that would, what that would answer would be, where is the slope to this line the greatest, right? So if you maximize that, maximizing g, it's the same thing as asking where is the instantaneous slope of x cubed largest. Or saying where is the rate of change, where is the instantaneous rate of change of x cubed largest, right? So, right, so that's not what that's also not what we're looking for. Madeline.
Okay, so I said that your domain has to be restricted to x is greater than 0 less
Sure,
than 1.
sure.
And then
Why less than 1? Didn't say less than 1.
oh well, I said it's less than 1 because any number between 0 and 1 cube anyways, I think their function is x minus x cubed.
Okay, so here's another function. F of x equals x minus x cubed.
And then you would like
And you
find the
maximize that.
find the global max of that.
Okay. Are there other people's ideas? Other ideas? Claire?
Could you do two functions, one is x and one is x cubed, and find the minimum of
Here's x.
x?
Here's x
Oh, wait.
cubed.
No, find the maximum of x and find the minimum of x cubed.
So you find the maximum of x. So here's one function, and here's another function.
Oh wait, but that wouldn't be the same x value, would it?
It might not be the same place. Yeah.
Okay.
Yeah. So you're saying let's find the max of x. First, there's trouble. There is no max, right? X goes on increasing forever.
Right. And doesn't x cubed as well.
X cube also increases forever and decreases forever. Right? So
Okay.
neither of them has a max. Right. Okay. So this one is it actually. This one is it. You say, well, I'm interested in the difference between my number and its cube. Right. I'm hoping that that number is as big as possible, right? I want the difference between x and x cubed to be as large as possible. And what you see is that I think Madeline, got onto this, right? Once you pass 1, what happens? Well, x cubed is actually bigger than x, right? So it doesn't make sense to consider anything past 1 because the numbers do not exceed their cubes after that point, right? At 1, x and x cubed are the same, and then after that point, the difference becomes negative. So you don't have to worry about what happens after 1. Okay, so let's do it. So let's maximize. So h of x is x minus x cubed. H prime x is 1 minus 3x squared. Right. And so our critical points are, what are the critical points? What are the critical points?
1/3 and all 30.
Right. So we want 1/3.
Yeah.
Right. X. It should be plus or minus, but we only want the positive one because we're dealing with the non-negative numbers. Right. And it's also 0, 0, and 1, but we can see that at 0 and at 1 the difference is 0. Okay. Okay. Is that the max? Maybe. Who can say yes or no at this point? Is it the max? Who can say it is and explain why it is? Victor.
So because the function of the derivative is a second degree polynomial and it only has 1 0, and since it's negative 3x squared.
Well, it has 2 zeros, right? At 1 over root 3 and 1 over.
Yeah, but we're only interested in
Yes,
the-
that's your. Okay, we're interested in this side.
So there's only that one point where it changes signs, and because it's negative 3x squared, that means that the parabola would be upside down, so it changes from positive to negative, which makes it a maximum.
Makes it a max. Great. So, so by the first derivative test, we know that the function is increasing before and decreasing after. So 1 over root 3 is the max. Right. Okay, is the max.
You just plugged it into the original function to find out that it was positive on one side, negative on the other?
No, we look at the derivative, right? So here the derivative is this 1 minus 3x squared, right? And you see what the derivative looks like. The derivative is 0 at 1 over root 3 and at negative 1 over root 3, right? And it's an upside down parabola, so you know that it looks like this, right? You know that the derivative looks like this.
Oh, okay.
Okay, so the derivative is negative here, positive here, and negative here, which tells me that my original function is decreasing here, increasing here, and decreasing here. Okay. You could have also done this just by plugging in points, because with the observation that we can just consider 0, 1, we know that the function has a global min and global max on that interval, and so right? Your critical points, remember, were 0, would be the endpoints, and this 1 over root 3. And at 0 and 1, the difference is 0, and at 1 over root 3, you get something positive. So that would tell you that 1 over root 3 is the max. Okay, so that's another way to do it. Okay. Any questions? Okay, let's go on to something a little more complicated. Okay. You have a square piece of cardboard, and the length is, the side length is 20 centimeters. The question is that here's what you're going to do. You're going to cut out squares of equal sizes out of the corners, and you're going to fold up the sides and make a box with no top. Okay. You're going to fold up. You cut out the squares, you fold up the sides, and make a box. What should be the size of the square to maximize volume of the resulting box? Okay, so write down the function, some expression for the function that you're trying to maximize. Or just take a minute and see how you approach this. You put in some, define some variables, make a function of those variables, and that you want to maximize.
It's already square or rectangle. The big one.
It's a square.
Okay.
The big thing is a square also. And you're going to remove squares. Okay, talk to somebody next to you.
I was thinking, where'd you get? I got exactly kind of what you got. So I was thinking, like the side that's right here, like this little square, right? Like here's one side, here's the other side, and here's the other side. So I guess with this side, you can make this X. And then I guess this, I think I want to minus X. So maybe 20 minus X. Oh. Yeah.
Okay, so first off, what kind of variable are you going to put on? is there anybody who would like to say what he or she did?
So I put variable x for both sides of the smaller square that you take off the edges.
Okay, so the side length,
Yeah.
like x.
On both sides. So like the length and the
It's a square. You're removing a square.
Yeah. So, then I thought that the length of, or the volume of the box would be length times width times height. So it would be, and the length, well, all of those I think would be 20 minus x, because it's the length of the entire square that you have now minus x, which is the box that you're taking, the little square that you're taking out.
You did 2x from both sides. 20 minus 2x.
Oh, smart.
So
Okay.
this is 20 minus 2x.
Yeah.
Okay. 20 minus 2x here. So you end up with this thing. This is the base, right? The base is going to be
20 minus 2x cubed would be the volume squared. Oh wait, the base would be 20 minus 2x squared,
okay,
Why?
because it's both sides.
right? This length is 20 minus 2x. This length is also 20 minus 2x.
Oh,
Right? So you have this. This is the base of your box,
Oh, and the height would be.
right? And what's the height of the box? X. Okay. So the volume, which is a function of x, called v of x, is going to be 20 minus 2x, quantity squared times x. Okay. Right. And then we want to find the x that maximizes that, right? Find x, that's sine length, that maximizes v of x, right? And so how do you do it? You go ahead, yes.
Sorry, can you explain again where the outside x came from? in
The
that?
outside x is the height of your box. So here's your box, right? You fold up these edges, right? And so how tall is your box at the end when you fold it? How tall are those edges?
Oh, I see. Okay.
Those edges are each x.
I see.
They're all x, height of x.
Okay, thank you.
Okay. Yeah, Kelly.
So to answer your question, is
Yeah.
to find the x, you would find the derivative of the volume?
Yeah. So let's take the derivative, right? And what do you get when you differentiate this?
2 negative 4 times 20 minus 2x cubed.
Negative 4 times 20 minus 2x
2x cubed.
cubed.
No, the cube is on x.
2x cubed. Oh, so you
2x, sorry, not 2x cubed, just 2x.
2x. Okay. Is that it? Don't forget, you've got, so be careful, right? V of x is x times 20 minus 2x, 20 squared. Right. So you need to use the product rule, say. Or you could multiply it out and just differentiate. Yeah, Asha.
Can I tell you the answer?
Yeah, okay, go ahead.
Negative 4x times 20 minus 2x
Negative 4x times 20 minus 2x.
plus 20 minus 2x.
Okay, I think that looks right. You've got the first guy, x, times the derivative of the second. Right, so let me slow it down. You look at the first guy times the derivative of this, right, which is going to be 2 times 20 minus 2x times negative 2. Right, plus the derivative of the first guy, which is 1, times the second. Okay, which turns out to be negative 4x 20 minus 2x times plus 20 minus 2x squared. Okay, and so you want to find where that is equal to 0, right? Where is that equal to 0? What do you do to do that? One way maybe to maybe let's factor out one of the 20 minus 2x's, say, because we have in each term we have a 20 minus 2x. So I'm going to factor that out. I get negative 4x plus 20 minus 2x. Right. Right, and so that's negative 6x plus 20 times 2 10 minus x. Right. The 20 minus 2x, I'm going to factor 2 out, becomes 10 minus x. Here I have 20 minus 6x.
You could factor 2 out of that as well.
You could, yeah. 4 10 minus 2x, 10 minus x, negative 3x plus 10. Okay. So what do you see? X is either 10, right? 10, or it is 10/3. So 10 10/3. Sorry, I messed up here. This is V, right? This thing is V. Here is V prime. Yeah, Victor.
So can you say that 10 doesn't work because for this to actually be a box, you have to limit the range of x between 0 and 10 on an open interval?
Yeah, I mean, I guess what becomes obvious is that 10 is going to be, it would be a minimum volume, right? That would sort of if you cut out things of like 10, then you're left with like nothing. Right. So you could say that 10 is our endpoint. Again, you could say that actually from consideration, we know that x has to lie between 0 and 10. And 10 is clearly the minimum, right? Because the volume of the box would be 0. Okay, right? And similarly, if you cut out nothing, if at 0, right? If you cut out nothing, then again the volume is 0, right? Because you just have this flat piece. There's no volume to it. There's only a bottom to your box, right? And so that tells you that 10/3 is going to be the maximum. 10/3 is going to be the maximum, or you could see it by you can see it just by consideration, or you can see it by using the first derivative test, right? Because again, what you see is that you have a v prime is a parabola, is a positive parabola, right? You're going to have a 3x squared. You have this 12x squared term on it, right? So you know it's going to be 10. You know it's going to be like this, right? So it's positive here, and it's negative here, and it's positive here. Right? So that tells you that your function is increasing up until this point, and then decreasing afterwards. Yeah.
So that's the graph of f of x, or v of x, right?
This is v prime, actually.
Oh.
Right. Remember, v prime is 0 at 10 and 10 over 3.
Oh, okay. Yeah.
Right? And it's here. This is v prime. Right?
Yeah.
V prime is a positive parabola. We see here.
So what can we tell about v of x based on that then? Just that it's
So that tells us that v prime is positive. So v is if you think about V, and with V 10, we see that V is increasing here and decreasing here. Right? So that tells us that 10/3 is the max.
Okay, yeah.
V is increasing here and decreasing here.
Got it.
Yeah. And, people often sort of get confused between V prime and V. Yeah. So remember, try to keep them separated. Right? This thing here we calculated was V prime, and it tells you about V, right? V prime was positive here, negative here, so that means that V is increasing here and decreasing here. Okay. Okay. So here is one that's sort of a classic.
I have a question.
Yeah.
Can you solve this without calculus?
Can you solve this without calculus?
It just seems like a problem you get in like hard high school. I don't know. Like, it reminded me of those word problems.
I don't know any way to do it without calculus.
Okay.
I don't know any way to do it without calculus. So okay, so if 8 minutes left, let's do this next. I have 2 problems left, but I'm going to skip. So I have sort of like a sort of hard one, and then this really famous one. So they're both about equally difficult, I'd say. We'll do the famous one because it's famous. It's a classic problem. You are making cans. Okay, you're making cylindrical cans. There's a fixed volume. So volume is fixed at there's some fixed volume that's called V naught. So here is R, the radius, and then there's a height H. The question is, what dimensions minimize the surface area of the can? Okay, so the can is just the shell of a can, right? It's like a soda can, right? It has sides, it has tops, it has top and bottom. Okay, but it's not a solid or anything like that. Because it's supposed to contain a certain amount of soda, and you're wondering what's the best can that minimizes the amount of metal that I'm going to use. Okay. And part of the problem is express answer with an H to R ratio. Don't worry about that part yet. Okay. Don't worry about that part yet. Once we solve the problem, it'll turn out that the ratio of H to R is something really nice. Okay. So we're trying to minimize the surface area. Okay. We're trying to minimize the surface area of the can. So I'll let you think about it for 1 minute. 1 minute only, and then we'll try it. Okay.
You want the circumference times that. To get the equal, yeah, you're right, actually.
Okay, so this one's a little bit tricky, but let's do it. Surface area of the can. So, or does anyone want to say anything about how to approach it? How do you solve this problem? Yeah. You guys talk too much. But nobody else wants to talk. Should I roll the die? See if anyone-
Asha, just pick Asha.
Asha. I always waste time trying to get the die. How much stuff do I have in here? 19.
Asha.
5, 10. Make the extra again. 5, 10, 15. I get close. That's clear.
Oh yeah, you said that.
Oh, you missed it. Dodged the bullet. Okay. Yeah.
So don't you find the surface, you find the equation for the surface area?
Okay. Yeah. So what's
And the
what's
volume.
Okay. So what's the surface area? Surface area is going to be what? Well, there's the tops and bottoms, so that's going to be 2 pi r squared. Right? 2 pi r squared, and then there's the side, right? Which, if you unrolled it, would make a rectangle, right? If you unroll the side, it would be a rectangle of height h, and of length, what?
Would that be the circumference?
2 pi r. Okay. So you have 2 pi r h. Okay, so that's your total surface area. Okay. And you want to minimize that, right? So you want to think of that as some function of r maybe, or h, whatever you want to think, right? And you want to differentiate it. But yeah, Sarah.
Wait, so why is it 2 pi r squared? Because it would be 2 pi r just like times 2. Oh wait, oh sorry.
The 2 pi r squared is the bottom and the top.
Yeah.
Pi r squared,
Okay.
and then you've got the sides. Okay. Yeah. Okay. So you'd like to differentiate this with respect to r, say, or you could differentiate it with respect to h, or which one? The trouble is that there are 2 variables, right? There are 2 variables. So one thing you can play at this point is let's get rid of one of the variables, okay? Because they're related, right? It's not like these are independent of each other. They can't vary independently of each other because the volume is fixed, right? So as the r changes, the h is dependent on it, or vice versa, right? So we know that that the relation is pi r squared h is that volume, and so for example, h is v naught over pi r squared. So we can use geometry to express one variable in terms of the other. Right? This is to eliminate a variable. Because at this point in your career, you're not interested in functions of 2 variables, although you will be, shortly. Okay. Okay. So surface area. Surface area is then 2 pi r squared h plus 2 pi r h. I'm sorry, 2 pi r squared plus 2 pi r v naught over pi r squared. Right. Yes. Hmm? Right. When you multiply, right, if you have a times b over c, it's the same thing as ab over c. So then you see that the pi's cancel out, one of the r's cancels out. You get 2 pi r squared plus 2 v naught over r. Okay, I just wrote down the same thing again. Okay, so now let's differentiate, right? So the derivative with respect to r is going to be 4 pi r. You got this 1 over r to the minus 1, so you get minus 2 v naught over r squared. Right? Setting that equal to 0, we get 4 pi r equals 2 v naught over r squared. Right. And so that tells us that r cubed has to be 2 v naught over 4 pi. Like multiply the r squared on both sides, divide by 4 pi on both sides. That's to say v naught over 2 pi. Yeah, go ahead.
When you found the derivative of that thing,
Mhm.
why didn't you have to do any quotient rule for that to be not in
You do. I mean, basically you do. But you could also think of it as r to the minus 1. Right? You have a constant times r to the minus 1. You're differentiating. So you're just differentiating this r to the minus 1, and so you get negative r to the minus 2. So you get negative the constant over r squared.
Oh, okay.
It's clean. You could use a quotient rule, but it's faster to do it this way. Okay, so what does that give you? That gives you that r must be the cube root of v naught over 2 pi. Okay, so that's the answer. Oh, yeah, Claire.
How do you know that that root is a max?
So you do the same thing. You can use the first derivative. You can use the first derivative test to show it.
Plug in r as.
So that's the 0, right?
Uh-huh.
And then you have to evaluate to the right and left. Let me get to the punchline, and then I'll talk to you after. Okay. So something cool happens. Observe. If we look at the ratio of h over r, what is that? That's going to be h. H was v over pi r squared divided by r again. So we get v over pi r cubed. Okay. Now if we plug this in, we get v naught over this thing cubed, right? Which is going to give us v naught dividing by v naught over 2 pi, right? And so what happens is you get 2. Right? So the ratio of h to r has to be 2. In other words, the height, for the ideal can, the height should be twice the radius. In other words, the height and the diameter should be the same. Okay. So the ideal can is actually a kind of squarish can, almost like a cube. At least in terms of saving material. Okay, sorry to keep you over.